Okay, so hopefully I've given you some perspective of what computer architecture is about today, and hopefully you all are excited about being part of this. But let's start with some fundamentals also. I'm going to give you some other perspective in a different way right now. I guess I'll ask you this question: what is this? And if you're a fast enough typer, you can answer it. Although I may not be able to see your answer. Okay, I don't see any answers in chat. Somebody answered it. Okay, they got it right. Yes, train station Stadelhofen. You may have seen this if you already taken my digital design course. Uh, and there's a reason why I put it, because I'm going to make comparisons to this architecture itself and hopefully take away some lessons. Basically, the answer is yes, it's Bahnhof Stadelhofen. It's a beautiful place, actually. Sometimes it's too crowded. Especially these days, things cannot be too crowded, as you can imagine. But it's also the first major piece of a famous architect, and I assume some of you know who that architect is. Anybody? But before we get into that, basically, this is a description of that. The train station has several of the features that became signatures of his work, this architect's work. Straight lines and right angles are rare, and that's true actually, which is interesting. Things are always bending in some way. And this architect is actually an ETH alumnus. He has a PhD in civil engineering, and he is Santiago Calatrava, and he built many things which we're also going to look at. But you can see that there's an architectural style, and it's good to compare the uniqueness of that architecture to some other architecture. So this is another train station. I took this picture from online, and somebody in my class later figured out that this is a station in Germany. I guess you can read something. There's some side channel information that's going on over here that you can figure that out. So it may not be the perfect comparison, but okay, it'll work for my analogy. This is basically a vanilla train station that's out there anywhere else in the world, I think, almost. And I think it's a bit different. Stadelhofen is a little bit different because it reflects a particular style of architecting a system, right? I mean, this is also a system that's being architected with some principles, and it has some other trade-offs that are made. But clearly, there's a difference in the style and trade-offs that are made, right? So it's good to keep that in mind. So this thing, what we're going to do in this course, examining ideas and different architectures and looking at different sort of trade-offs and developing new ideas and better architectures, is not so dissimilar to what I'm just talking about here, comparing two different train stations. So this is another train station, at least something that houses a train station underneath. It's the Oculus. Okay, I won't bore you with asking all these questions over here. This becomes much better if we're in the same room and interactive clearly. But this is Oculus. It's in the middle of New York City, and clearly this has a similarity to Stadelhofen actually, because Stadelhofen is somehow modeled after a bird, and this also is somehow modeled after a bird. So this is also so Stadelhofen was the first major piece of Calatrava. This Oculus is actually the masterpiece, let's say, or it's considered the masterpiece of him. And clearly he had some idea of what it would do, basically design, resembling a bird being released from a child's hand. And clearly the roof was originally designed to mechanically open to increase the light and ventilation. So there are some design constraints, as you can see. People are going to be in the space. And those design constraints may or may not be satisfied, right? And clearly some people like it. This actually cost people a lot. I think we will see this cost. If we don't see it, I will let you know. But you can see some praise over here, which is, the last line is very interesting. It's a pleasure to report for once that public officials are not overstating the case when they describe a design as breathtaking. So that's it also clearly has some satirical nature to politicians, as you can see. So of course, any architecture is not immune to design constraints. So you can see design constraints actually curbed the design here. Security is an important design constraint, as we will cover in this course also. So somebody said Santiago Calatrava's bird has grown a beak in the name of security. Its ribs have doubled in number and its wings have lost their interstices of glass. So they had to eliminate glass, you can see, at some particular places. And ... Now it may evoke a slender Stegosaurus than it does a bird. And if you're curious about what a Stegosaurus is, I'm assuming this person is not using it in the best possible context when they're criticizing the design to resemble a Stegosaurus. Okay, anyway, so there are a lot of jokes clearly, but design constraints are real over here. And then the design was further modified to eliminate the opening and closing of the roof mechanism because of budget and space constraints, which was really envisioned by the architect. And this also shows us that there's constraints: space, chip area, budget, cost. Cost is always a constraint, actually. If someone tells you cost is not a constraint, they will hit that constraint at some point. They may not think it's a constraint, but they will hit that constraint. And it turns out this is the most, at that time at least, the world's most expensive transportation hub. It's almost close to $4 billion. So it's not very cheap. So even though it was not very cheap to begin with, you couldn't do everything you envisioned to do in the architecture. And that's true for real computing architecture also. If you design an architecture, you may envision a lot of things. In the end, you may end up cutting things. That's really true. In the end, for various reasons, you may want to push out the chip to the market because your customers are not waiting. Otherwise, you're going to lose a lot more. And you may actually not put in some of the security features. It's different from this over here. You may not actually decide to put in some security features over there. That's possible. Or you may not be able to test things as exhaustively as you should, so some bugs may slip. Or you may actually say, okay, I'm not going to have this feature anymore. So what you usually do is whenever you design architecture, you have a priority list of features and you try to get the highest priority features in, and many of them always get left out, in my experience at least. Okay, so that was the point of this basically. Design constraints, no one is immune to the design constraints. And this is prevalent in the architecture space. That's very much prevalent in the computer architecture space also. So another question. This is, I don't know if anybody is going to answer this one, but what is this? I guess I'll give you 2 or 3 seconds. See how fast you can type. Or I cannot guess how, if nobody answered, I cannot guess if you can type, of course. But okay, but basically this is another thing. And it's falling water. It was close to Pittsburgh where I used to teach. And it's the masterpiece of another famous architect who is Frank Lloyd Wright, and this house, it was built as residence for Kaufmans, actually, who were a wealthy family close to Pittsburgh. It's a beautiful place, actually. I went there many times while I was there, and clearly it has received a lot of praise, maybe less criticism at the time. Times are changing, so criticism is easy to, I guess, throw at people today on Twitter and anywhere. But basically, it had a similar issue. It's basically, it was designed to be much more ambitious, but at some point Kaufman said, we're not paying you anymore, stop. And he stopped. And he stopped at a point that was good, at least reasonably good, as you can see, although there are some things you can see that they were not completely finished, and they need to restore it once in a while, clearly. But basically, this was too costly also for its time. Okay, so I would say your first computer architecture assignment is going and visiting Bahnhof Stadelhofen and looking at it from a different perspective. I think this is best done after you think about the trade-offs that we examine a little bit. You can repeat it for Oculus, you can repeat it for falling water, and hopefully you will never see architecture the same after this course. I would suggest appreciating the beauty and the out-of-the-box and creative thinking, because there is a lot of creative thinking and that has gone into actually the Bahnhof, their strengths and weaknesses and goals of design. You can read about them. You can also think about them. You can derive principles on your own for good design innovation, and this is possible. You may not be an architect. That's fine. You may be a computer architect, but you can actually still reasonably evaluate things. Evaluation is going to be important actually in this course also, how we evaluate computing architectures. And feel free to send me messages about this. I actually still receive messages from past students who have gone to Oculus, for example. I receive pictures from them, which is interesting. And you can apply what you've learned in this course also to them. And hopefully you will be able to think out of the box. But let's take a look at one example. We're not going to do this exhaustively. We want to find the differences between this and that. And this is this, which is Bahnhof Stadelhofen, and that is that, which is a random Bahnhof in Germany. So what are the differences? Again, I'm not going to bore you with that clearly. There are a bunch of differences, but you can see there are no straight things here. Everything is curbing over here in Stahlhofen. So that's one of the design choices, and this thing resembles a bird again, or ribs of a bird, as you can see over here. So there's some resemblance. So clearly you can list them later, but my point is there's always an evaluation criteria for the design. True for architecture, true for computer architecture. Functionality, does it meet the specification? How reliable is it? What is the space requirement, area requirement? What is the cost, expandability? Can it be used for other purposes? What is the comfort level, happiness, aesthetics, and who knows what else, right? There's security clearly somewhere over here that I didn't put, but all of those exist. So how to evaluate goodness of design is always a critical question, and we will struggle with that at times, but there are clearly some metrics to look into that. And I will also say that no design is good at everything. This is something that we will talk about in memory, for example. There's no single memory type that's good at every single metric. There's no single processor that's good at every single workload or metric. It's always a trade-off, and it's really important to understand those trade-offs here. And we're going to cover this course from the perspective of those trade-offs. Now let me pose you another question. How was Calavatra able to design especially key buildings? You can have many guesses in terms of this, but it's not so much different from designing a computer architecture in the end, basically. I think I will point out especially the last two over here, which is principled design. So he was a very principled designer. That's why he was so successful. And we will at least flash the principle in a little bit. And he was also very strongly committed to understanding of basically the use of fundamentals. So he started very fundamental and applied the principles on top of those fundamentals. I think these two are for sure. But he also did other things, of course, hard work, perseverance, dedication over decades. He built some experience. It was creative, out of the box. He had a good understanding of past designs, good judgment and intuition, and he had a strong skill combination in math, architecture, art, and engineering. And he was probably lucky to be supported with funding, and he had the initiative to actually get the funding. So actually these things work together probably. And hopefully I think you will be exposed to a lot of these in this course, and hopefully develop and enhance many of these skills in this course. I think good judgment and intuition is very important because not everything that's in architecture is science, some of it is art. Because how do you actually guess what's going to happen 10 years down the road, right? Because some of the things that you design are going to be executed 10 years down the road. Now, some of it can be science because you can do modeling and prediction, but not all of it can be science because you don't know exactly what will happen. If you knew exactly what would happen in 10 years from now, that would be really nice actually for many, many things, right? Okay, so basically these are the principles. This is in Calatrava's words. To me, there are two overriding principles to be found in nature which are the most appropriate for building. One is the optimal use of material, and the other is the capacity of organisms to change shape, to grow, and to move. So a lot of his works actually open up, for example. And other folks say that these are inspired by natural forms like bird wings and human body. This is another example of Calatrava architecture, which is in Lisbon. That was the first place I visited in Lisbon, actually, after I went there by plane. But you can see the anthropomorphic design over here. They actually call it zoomorphic architecture. There's a loose Wikipedia article about it. But it is based on some principles. And this one reminds me of a bird. For other people, it may remind of a dinosaur or something else. This is another one in Sevilla. It's like a pigeon, as you can see. For other people, it's harp. But I guess it was meant to be a pigeon. Okay, another quote from another famous architect, which has very similar properties actually and similar success, is Frank Lloyd Wright. He basically says architecture should be based upon principle, not upon precedent. Basically, precedent is what comes before. You should understand it, but not replicate it. Basically, design in a principled manner. So as a result, he did not design this house, which is a classic American house in the woods. Instead, he designed this masterpiece, as you can see. And it's based on some principles. Organic architecture is a principle over here. And this is another view of that piece, basically. You can see that it's in harmony with the nature over here. Actually, these cantilevers over here are imitating the waterfall the building is constructed on. Okay, let's yet another view. Okay, so let's get to the high-level goals of this course. Basically, we would like to understand the principles and the precedents in this course as much as possible. Architecture is a very wide area, especially if you expand it the way I expanded it. So we'll cover examples, of course. We won't be able to cover everything comprehensively, but hopefully we'll cover important examples that would be useful. And hopefully based on such understanding, this will enable you to evaluate trade-offs of different designs and ideas. enable you to develop principled designs, enable you to develop hopefully novel out-of-the-box designs. And the focus is on principles, precedents, and how to use them for new designs in computer architecture. My PhD advisor was E.L. Pat, who is this person over here. Basically, he's a very famous computer architect who has, with his students, invented a lot of the dynamic scheduling mechanisms that went into Intel Pentium Pro, a lot of out-of-order execution, superscale execution, branch prediction, all of that, and together with precise exceptions was part of the HPS model he invented, and also branch prediction mechanisms. But he basically says the role of the architect is looking everywhere. Basically, you have to have eyes everywhere. You need to, and this is my re-rendering of what he has said with my commentary and experience, of course. Basically, you need to be able to look back to the past and understand and figure out what you've done wrong and what has been done wrong, analyze and evaluate it, understand the workloads and trade-offs. You need to be able to look forward to the future and be open to it. You need to be the dreamer and listen to the dreamers and push the state of the art, evaluate new design choices. If you actually keep producing the same thing over and over, that will not look forward. You need to look up, basically what we've been discussing, top, understand what's happening in the software problems and their nature, and you need to look down, understand the capabilities of the underlying technology. Because if you do all of these actually really well, then you can actually change things really, really strongly and in a bigger way. Okay, we can talk more about this, but I will not talk, but I will give you some takeaways basically. I think being an architect is not easy. You need to consider many things in designing a new system. You need to have good intuition and insight into ideas and trade-offs. And as a result of this, not many people are architects, right? That is true actually. If you look at computing system stack, architecture is actually a relatively small group of people because they need to do a lot of different things. I mean, I'm not saying any part of the stack is easy, but this part is actually so critical to a lot of the things at the top as well as the bottom that not many people actually do it. But it's fun and it can be very rewarding, and it enables a great future in the end, because many scientific and everyday life innovations would not have been possible without architectural innovation that have enabled very high performance systems and very high efficiency systems. My cell phone would not have been possible with good architectures, for example. And there are many other examples, self-driving vehicles, hopefully genomics accelerators. If you have a COVID-19 testing cell phone, that would be in good part of an architect in the end. And hopefully this course will enable you to become a good computer architect. So I'll take a few more minutes just to finish this thought. Basically, we're going to cover hardware-software interface and how it affects the software, higher levels, as well as the lower levels. So basically, you've hopefully taken a computing systems course. You've hopefully taken a digital design course. If you have not taken it from me, you can actually look at the lectures. My course is a little bit different from digital design in general. We don't go into as much detail and nitty-gritty of digital logic, but we actually cover a lot of paradigms. So in the computing systems, we normally look at how does a system execute the program, assuming something's in the digital logic. You don't go below the interface. In digital logic, you actually, in a traditional digital logic course, you talk about logic gates and wires and how to build a computer, basically. An architect is really thinking about a computer that meets this system design goal. So the architect really needs to know what's going on in both parts, because his or her choices critically affect both the software programmer and the hardware designer in the end. So that's why levels of transformation is very important, basically. This is Richard Hamming, who is a Turing Award winner. He developed Hamming codes. And one of his favorite quotes is, the purpose of computing is to gain insight, not generate numbers, basically. So we gain and generate insight by solving problems, and we ensure problems are solved by electrons. I'm not going to cover everything over here, but this gives you an overview of the transformation hierarchy. This was covered in digital design and computing architecture. Basically, we define what these different things are, and you can look at the slide afterwards, after the lecture, or you can also watch the lectures. But basically, all of these pieces are there to ensure that the problem gets translated to electrons. And I would also recommend that you take a look at Hamming's famous work on error correcting codes. It introduced the concept of Hamming distance, which is one way of actually matching different strings, but it's not approximate. It basically tells you what are the differences between strings. It doesn't really account for how many insertions are there, how many deletions are there, how many substitutions are there, but it just basically tells you how many locations are there in which these two symbols of equal length strings is different. And he developed a theory of codes that are used for error detection and correction also. And I will also recommend that you take a look at his talk on you and your research, because it has very good insights in terms of how to do research. He actually did research at Bell Labs for more than 30 years, I believe. And he developed insights on how to be a good researcher. And I would definitely recommend that work. So I think, as I mentioned, a user-centric view may be a good view of these transformation layers. So why are these transformations layered there? Basically, these levels of transformation are actually good because they create abstractions. What's an abstraction? Basically, a higher level only needs to know about the interface to the lower layer. They don't need to know about what happens at the lower level and what is implemented there, which is really nice because now you can keep your sanity, right? If you're a programmer, you don't need to know about what goes on underneath in terms of compilation, in terms of systems, in terms of how the hardware executes those programs, right? At the high level, you're happy. Exactly what I said over here, right? Abstraction is really good for improving productivity. You don't need to worry about decisions made in underlying levels. You don't even need to know about them, right? Like programming in Java is better than programming in C, which is better than programming in assembly, which is better than programming binary, which is better than programming by specifying the control signals of each transistor every cycle for productivity purposes. Right? Performance is a different issue over here. But for productivity, if you had to actually dictate what the input, what the control signal of each transistor should be as a programmer, the high-level programmer, good luck programming sophisticated programs, right? You will not get there anytime soon. But then why are we going to break those abstractions and try to understand across the stack here? First of all, I think I've already given you the answer from an applications perspective. We really need to optimize across the stack to get highest efficiency and performance. But there's another reason, which is when you run into problems. And most people run into problems. They write software that doesn't run fast. So as long as everything goes well, not knowing how it happens underneath or above is not a problem. But what if the program you wrote is running slow? What if it's not running correctly? What if it consumes too much energy? What if your computer just shut down and you have no idea why? And what if someone just compromised your system and you have no idea how? And on the other side, what if the hardware you designed is too hard to program, like the cell processor, like potential processing in memory engines? What if the hardware you designed is too slow because it doesn't provide the right primitives to the software to actually exploit the hardware? And what if it's not reliable? And what if it doesn't provide the right abstractions? And finally, what if you want to design a much more efficient and higher performance system, which I already said before? Basically, these are the reasons to cross the abstraction layers, because if you don't have the answers to this, then you're at the mercy of someone else. And someone else may not be actually experiencing the exact same problem. So you will not know enough and you will not fix things fast enough if you don't know the answers. So the two key, I believe a computer architect is actually comfortable in having these answers. Maybe not all of them in all complicated systems, but at least understanding fundamental trade-offs here. But basically, two key goals of this course are to understand how a processor works underneath the software layer and how decisions made in hardware affect the software programmer. So we're going to look at both sides of the coin. And hopefully you will become comfortable in making design optimization decisions that cross the boundaries of different layers and different components. So I think I'm going to stop at this point. At this point, basically, I was going to give you some examples of crossing the abstraction layers. And I'm going to start with an example in multi-core systems, which leads to memory performance attacks. But I think we're going to pick up at this point tomorrow and talk about memory performance attacks and hopefully talk about DRAM refresh as well.